file that I made for you, lecture 9, but actually it's a combination of some lectures here. So one option is I go back and bring it, or we present from this one, and then I will combine later, okay? So we present, this is my presentation in Cebu, and your lecture today is actually a combination of 2 of these lectures. So let me start with this one, importance of section capacity and ductility, and then I will go to PVD, and then your lecture is actually a combination of these 2. So I will upload lecture 9. Okay, let me start with this one. You remember this graph? How many times we have seen this? Many times, right? So today we want to link this graph or this curve to performance-based design. So performance-based design, the main difference, as you know, between conventional design and performance-based design is, what's the main difference? The conventional design or the code-based design up to only considers this portion and a failure point. But the performance-based design considers the entire response history of the structure, of the elements, of the cross-section, and of the material. So for that purpose, the ductility and the cross-section moment curvature and confinement, they are very important, and we have discussed this already. So if I just repeat this that we have already seen in the previous course and today, and that we started, the design process started with the limit on allowable stresses. It used to be called working stress design. So that means people thought that if you limit the stress, everything will be okay. So if you limit the stress not to be over 50% of the yield stress, then structure will be fine. And later they found that that is not a good way to look at things. And then after that, more explicit factor of safety came in, which applied to loading, applied to materials, applied to different type of action. So a lot of capacity factors come in, not only working stress only on the material. So this complicated explicit factor of safety has become so complicated now that in the building codes there are many factors, especially Eurocode and other codes. They have so many factors that you need to multiply before you get the design done. And then ultimate design was formulated based on that, and now it has been becoming more and more complicated because more and more factors are coming in. I will talk a little bit more about that. Then after that, this next stage was the difference between brittle and ductile behavior. So this was an important observation that people start to know that, okay, ductile and brittle behavior cannot be treated in the same way. So these factors should not be applied to them in the same way, because the consequence of a ductile and a brittle behavior is not the same. And this was an important recognition, and it took many years for engineers to recognize this aspect. Then from that came the capacity-based design approach, based on this idea that the brittle and ductile behavior are 2 different things and can be handled differently or have different meaning or different consequence. The capacity-based design came into being, and we have talked about that. And based on the capacity-based design, the next step was performance-based design. That means we look at the overall performance. We don't look at individual factors. We don't look at necessarily how we multiply the loads or the materials or something. We look at the final outcome and the final performance and see whether it is acceptable or not. So certain types of performance then start to come up. What is important to structure? What we should be looking at? So those performance indicators, or sometimes they are also called KPI. If you work in many industries, even when you hire a contractor, or I remember when you were not here at that time, we hired a company to manage AITs on resources called Sodexo. So this was about 7 years ago, 8 years ago. So before that, AIT used to do everything. So it was a prescriptive. That means we had people and they were given the instructions, let's say cleaning people, clean the window every week. That's it. So they will come and clean. But there was no requirement how clean the window should be and what was the outcome of that process. So people just do the process and they get paid. But the quality of the output was not measured. And AIT spent a lot of money doing that. So they said, okay, let's give it to some company to do all of this stuff. And then at that time, I was also involved to set the KPI for them. How will we judge that the company performed very well? We will not give them any procedures. We will not give them anything. We will just tell them, this is the money. This is what we expect from you. We will measure these in the end. If this is okay, we don't care how you do it. And that's the concept of the KPI, key performance indicators. So the whole industry and many people are now always working on KPI. For example, faculty and staff in AIT have KPI. So for me, there's a KPI. So when my contract goes, so anybody contract goes to review, they have a certain KPI. Did I meet those KPIs or not? When I come to the office or don't come to the office is important, but not critical. We don't have, in AIT, we don't have those, time, what is that called? Where you use punch cards, right? We don't have that. But everybody has KPI. So they expect us to finish something and those are measured. And if they are not measured, you don't get promotion or you don't get your contract renewal or that's it. So this idea of KPI has now come to structures that instead of telling how to do something or put limits on this and this, just define what you need and measure the structure for those KPIs, and that is performance-based design. And after that, we are talking about risk-integrated design, holistic design, next step. So today I want to talk about PVD because now this is becoming very popular, very important for many industries and including structural engineering. So this is the overall framework of PVD. I have shown you this many times. You have seen it in many places also. And the idea is that you link the performance with the hazard and the outcome together into one area. So if you look at it carefully, you will find here, this may be called vulnerability. That means the structure's weakness. The structure's weakness due to some hazard. So this is hazard or loading. So when the loading increases or the hazard increases, the structure becomes more vulnerable and finally at some point it will collapse. And on that curve, you can then define your KPIs. That I want my structure to be here, here or here corresponding to a certain hazard level. So the relationship between hazard and performance and vulnerability, they are defined. So consequences and the hazard and structure's performance, they are linked together. This is something that people can understand. Many times, as I told you many times, structural engineers, when they are in public, they talk about bending moment and forces and something like that. Public and other people, they don't care about that. They care about, is my structure safe or not? This figure they can see. Safe structure, less safe structure, structure collapsing. So if you can tell them that your structure is here or here, of course, if you tell them your structure is here, they will say, of course, no one will accept that, right? But here or here, they can choose corresponding to a certain level of hazard. And you can say if you put more money, you get this. If you put less money, you get that. If you put, so you can talk about the performance and cost and time and everything on this curve, which everybody understands. And how we go from, and as you can see, this is a nonlinear curve. So automatically, the code-based design or the traditional design will not work to get this information because they only work in this region. They do not give you the information of the structure's behavior beyond the design level, which is a theoretical level. So to understand performance-based design, we must first of all understand that we need to go into nonlinear response range. It cannot be done on a linear case that we normally consider. We also have to remove all factors because factors are arbitrary. they do not have any real meaning. So that's why you also remember we studied in the last year that there are two ways that you can do structural analysis and design. One is you start from the loads and you go to these material stresses. And one is that you start from the material response and go to the load capacity. So now we are talking about this. This is traditional design, code-based design. It goes like that. Performance-based design, it reverses the process. It starts where code-based design will finish. So once you finish the design, then you can check the performance of that design. And then you can verify the performance is okay or not. So this is still done, but after you finish, then you start again with the output and go back and compare the input. So the previous slide is actually a comparison between input and output in that way, right? Hazard, loading, and performance, they are directly compared. And this is what this can do. You start from here, applied loads, hazard, and you calculate design, reinforcement. You put it back from the material, section response, member response, structural response, load capacity, and then you compare them together, and then you can say whether I am okay for this or not. So response and hazard are compared directly. This concept was first introduced many years ago and used to be called pushover curve. How many of you are familiar with pushover curve? One. Okay, so I will talk about pushover curve today because this was the starting point of the performance-based design many years ago. So let me skip a few things. Okay, you remember this slide also. This is from the book. So we talked about how we can integrate the response of everything. And this is very essential because if we want to do a detailed performance-based evaluation, cross-section response is the most critical one out of that. Because from material, you go to cross-section, and you cannot go further unless you calculate the cross-section response correctly. So that is why this development of this integrated theory that we talked about in the first course is critical to the application of PBD, or performance-based design. And at that time, we talked about two phases. One was about capacity, the other one was about moment curvature. And now we are talking about the second portion, which is about moment curvature. So you remember this diagram, right? So we developed a theory that will handle any cross-section for any deformation. So we are starting with the material, known material and known strain configuration, and then we use these equations to predict the response and also to predict other things like moment curvature and many things that you have seen in the last course. So what you studied last course is very, very important for doing PBD or going forward with that one, okay? So we talked about, so codes use factors, but in PBD we don't use factors. So we talked about this one. Let me just skip. So we can generate these capacity interaction surface. So the problem, as I mentioned to you last time, and now I want to emphasize that one more time very critically, that this interaction diagram or this assumption of a known strain is not a real case. I told you at that time also, and I'm telling you again, this condition of this ultimate or failure surface never ever happens in a structure, because this is an artificial condition. Why is it artificial? Because it corresponds to dead load multiplied by 1.4, live load multiplied by 1.6 or 1.7. Why would dead load be increased by 40%? Why would the live load be increased by 70% in reality? Cannot be. Live load is live load, dead load is dead load. So this condition cannot exist because it's an arbitrary design level which we have created just to check something, but it is not real. So we cannot rely on this information to determine the performance of a structure. We need to compare real loading with real response. Then we will know if they're okay or not. So that is the reason that this is not useful. This is useful for the first case where you design something, not useful to do the performance evaluation. This is a capacity surface. So all these are not useful. This is good for design, but has no meaning because these factors have already been multiplied. The forces have been multiplied by arbitrary factors, and they are not real. So ductility we talked about. Now let's concentrate on this. I just want to stay on this slide for maybe 5-10 minutes today, because this is the summary of everything that we do in performance-based design. So I think I showed this last time, but we didn't spend enough time, so let's now get back to this one. So basically what we are saying is that we start now the performance-based design from two directions, two ends, hazard end and from the material or the capacity end. So this is the capacity end, response end. So you have the steel, you get the stress strain curve for steel. You have concrete, you get stress strain curve for concrete. If you have confinement, you modify this one here. So you get the basic material response either from the lab or from the known equations or known models for materials. After that, you assign those or put those materials and into a cross section. So now you have a certain cross section, let's say rectangular cross section, circular cross section. You have reinforcement there, you have concrete there, and then based on that you generate moment curvature curve, not capacity curve, moment curvature curve, because moment curvature curve tells you the entire history, response history of the cross section, not just one arbitrary point. It can tell you the curvature of this cross section for any moment, factored or unfactored. So that means this is the response, total response property of the cross section. The moment on this cross section cannot be outside this curve response. So that means this is a property of the cross section. The moment curvature is a property of the cross section, and based on that property, which is based on the material and cross section property, so this is intrinsic property. Based on that, we can then say, okay, this is my moment curvature curve for every cross section. Actually, we can generate this curve for every cross section if the reinforcement is changing. If the reinforcement is same, you will have the same moment curvature curve. But if the reinforcement is changing in the beam, every cross section will have a different moment curvature curve. Now let's say that we say that, okay, this is a beam, but because the maximum bending moment is going to be here, or in a column, maximum bending moment, let's say here, we say that the yielding will happen here. We assume that the rest of the beam will remain elastic because it will start to yield at the location of maximum moment. So we assume that the beam will yield in this portion called plastic hinge. That means it will become plastic when if we keep increasing the load, at some point it will become plastic. It will start yielding here. So this yielding is related to a certain pattern of deformation. Let's say we apply two forces here, and then because of those forces, we push the frame. And because of that push, the bending moment will be generated, rotation will come, and that rotation, that moment, that curvature, now we can relate them together. So this is the curvature because of the forces, and that is the capacity curvature inside. So now you have two quantities, right? Outside and inside, both are there with you. So you assign this property to this hinge. In fact, you multiply it by a length called hinge length, and you convert that into moment rotation curve rather than moment curvature curve, because moment curvature curve is for each cross section. But we assume that the beam is yielding for a certain length, because not one cross section cannot yield alone. Next cross section will also yield. So we assume that the beam will yield in a certain yield length, normally called plastic hinge length. And this is equal to typically depth of the beam. So if the beam is 500, the length of the hinge will be also 500. So we integrate or multiply this moment curvature curve by the hinge length, and we get moment rotation curve. So now we get a relationship between bending moment and rotation. Now if you remember, the Dr. Panchit's class, he told you about the relationship between the rotations and moments, right? And from the analysis point of view, that means there is a matrix that relates the actions with deformations. So the action deformation matrix, which is bending moment and rotation, axial force against axial deformation. So that relationship will determine how much rotation will be generated because of this loading here, right? But then that rotation cannot exceed the rotation capacity of that cross section. If it exceeds, then it will start to yield. It will start to become plastic. So that means you cannot apply these forces unlimited. That is why if you plot this deflection of the total frame against the total force based shear, you will get that curve. This is called pushover curve. That means you are pushing the structure, and because of that push, the corresponding plot between the push force and the deformation are being plotted. And this is called pushover curve. This is very important term that people use, that we are pushing the structure, and because of that push, we are getting a certain displacement, and we can plot that force, total force of push with the displacement, and we call it pushover curve. Now this is one side, so this is coming from the capacity. Here we don't know the actual loads. We just apply the load and we keep pushing until we cannot push anymore, until the structure fails, right? So we get the theoretical capacity of the structure to take those forces. So we keep this as a property on one side. So this is generated, pushover curve is generated starting from that, and we put any load here, certain loads here, and we push it. These are not real loads. These are some assumed loads that we will push. So we get a relationship between that and that. And then we stop here. Then we go to the hazard side, the other side, forces side. Where is the force coming from? Earthquake, in this case. So this is the earthquake natural period and response spectrum. So you know response spectrum, right, from the first Penning's class. So response spectrum is a relationship between the spectral acceleration and the natural period. So from that, we can convert that into ADRS format, which is the spectral displacement and spectral acceleration instead of natural period. So this can be transformed, same response spectrum can be plotted in a different scale in which you have displacement on one side and acceleration on one side. Spectral displacement and spectral acceleration are plotted on one scale. So this curve looks something like this, and you get different curves for different damping ratios. Each damping you get different because the response spectrum depends on damping. So when you have 5% damping, you get one curve. When you have 2% damping, you get another curve. So the response spectrum coming from the response spectrum curve for the earthquake, particular earthquake hazard level, can then be converted into a spectral acceleration and spectral displacement curve. Now, if you look at this one and look at this one, they are on the same coordinate system. That means displacement in one direction, force in one direction. So we can put them together. It's just like two slides, two papers, and then you bring them and overlay with each other. And when you overlay that, they will intersect at some point. That point is called performance point. That means that is the actual loading and corresponding actual performance. Because loading is coming from earthquake, performance is coming from property, wherever they intersect. So if the earthquake is stronger, it may intersect here. If the earthquake is weaker, it may, so if the performance is low, it may intersect here, which means large displacement, small force capacity, right? If the building structure is very strong, this curve will be high. That means earthquake is under that, easily, no problem, no yielding. So this relative plot of the two can tell you the whole story Who's stronger? Who's winning? Earthquake is winning, or force is winning, or capacity is winning. And at some point, they intersect. That means there is a intersection point where both of them kind of balance out. That is performance point. But it is not essential that you always get a performance point. You get performance point for well-designed structures. If the structure is poorly designed, this green color is here and hazard is above that, you don't get a performance point. Hazard wins and your structure will never reach that earthquake level and will fail before that. If the structure is over-designed and these hazard levels are below that, that means your structure remain elastic and it's over-designed. So this comparison between the hazard plot, hazard spectrum, and the response of the structure together on one graph is the key to performance-based design. And here you can decide what displacement do you want them to intersect. So here, let's say the displacement, spectral displacement calculated to be 200 millimeter. You can say this is too much. I only want 100. So what do you do? What do you do? Yes, we increase the reinforcement or confinement or something, so the moment curvature curve is modified and you get better. So that means any change you do on steel or reinforcement material or cross-section or amount of cross-section will change the moment curvature curve, which will change the moment rotation curve, which will change the pushover curve, which will affect the performance point. So that there is a direct relationship between performance and your design. So your design can be actually now compared. A good and a bad design can be compared easily. Where is the performance? Which one is giving a better performance? That means smaller displacement or desired displacement, right? So this whole process of linking the hazard with the cross-section and structure and everything is new, relatively new. If people did not think, because we didn't have tools to do this kind of thing. So for a long time, this procedure of pushover curve has been used, but then many people, as you know, like anything, when you develop something, other people criticize. Somebody finds fault with and of course, many people find a lot of faults with this approach, right? First fault number one, can anyone guess? What is the biggest fault in this? Come on, think, people. You cannot find any fault.
Something about response spectrum.
The whole procedure, the whole concept of pushover. There are two basic faults here. In fact, three. Let's talk about one. Think. Don't believe other people. Okay. Fault number one is that this is a static pushover method. That means it is based on response spectrum, not time history. So it cannot accommodate the varying ground motion changes. It is only giving you the performance for a given force pattern, which we applied here. If you change the force pattern, this curve will be different. Then performance will be a different pattern. So this is corresponding to a particular load pattern that you have to assume in the beginning. That's the problem number one, because you cannot then use it for varying forces which are varying this way and that way, and also for different types of ground motions. That's problem number one with pushover method, that is it corresponding to a known force pattern, which is not that great. So which force pattern people use? Any guess? What is the force pattern we use? Actually, we can use any. This is only 2-story, let's say 3-story. So what pattern you will use for forces? Because these forces have no value. There's just a pattern because you have to push them. So first 1 ton, 2 ton, 3 ton, 4 ton, total force. But this pattern, how much is F1, how much is F2 of this V is important. How many percent you apply here, how many percent you apply here, how many percent you apply here, because this is a plot between total base shear, total force versus displacement, not individual force. So that means the pattern is important. So can anybody guess where is this pattern coming from? No equilibrium, there is no equilibrium concept here. Modal. This is the modal pattern, modal deformation pattern. So this is corresponding to, this deformation is coming from the modal deformation pattern. So you take that as a starting point, and from that pattern you reverse calculate what forces will be required to produce a deformation consistent with a modal deformation. So then the question is, which mode? Mode 1, right. So this is second problem with this method, that it is only good for one mode. But in tall buildings, higher modes and multiple modes are important. So the method becomes not so useful. What is the third objection? Big objection. Cyclic degradation. If you remember our blue curve, it goes up and down. This is only based on one direction. It does not include the cyclic damage of the structure. So the damage of the structure due to cyclic loading is not apparent in the method also, right? So these are the main three objections. There are many, three objections. First one, it is static, not dynamic. Second one, it is corresponding to a certain mode, not all modes. Third one, it doesn't include the cyclic degradation or hysteresis, energy dissipation in the model. So these are the three main shortcomings of this method. But it's okay, because people have to start somewhere. At some point, this was very popular. We still use it. It is still very popular. Why? Because after that, at least 30 different pushover methods came up. Everyone rushed to do a PhD or a master thesis on improving the pushover method and removing some of the problems. And I remember about 5 years ago, I offered a thesis to one student to check all of the methods and compare them against the real one. Her name is Amelia. So we published a paper also. So we have found that there's so many methods to do pushover, right? So some try to correct one problem, some try to correct another problem in a different way. So one problem, somebody try to correct this way, that way. So we have all kinds of methods coming up. Multi-mode pushover method and adaptive mesh pushover method and this pushover, all kind of methods, right? Just like confinement curves. So many confinement curves, confinement models. Same thing with the pushover. So many pushover methods came into being. And then it became popular, and then slowly they died off. And now 2 or 3 remain that we still use. One is called multi-mode, and we sometimes use it. And even this can be used for single mode pushover for small structures and for understanding the behavior of the structure. So that is the starting point of the performance-based design pushover analysis of pushover. And this performance point was very interesting. You can clearly see. And if you make any changes, you can see the shift in performance point, right? So so in that performance, obviously, the most important thing is ductility, because you cannot have good performance of a structure unless you have ductility, because this performance intersection normally generates because we have ductility. Otherwise, you cannot intersect here. It will be not good. So that's why the ductility was very important. I talked about it in the first course. You remember I said, whatever we are teaching now, you will need it in the next course. So now I'm trying to link the two courses together so you know the importance, why that was so important. So the cross-section response is needed to generate moment curvature curve. Moment curvature curve is needed to generate the moment rotation curve, which is needed to generate the cross-section response. So ductility ratio and ductility demand, all of that, ductility uses we have already. So let me just, I think, stop here and go to the second presentation. So this is the presentation about the performance-based design. And again, I think I have shown this slide many times to you, right? And I explained to you that this is what happens in a building when it is subjected to earthquake, even if it is designed to building codes. And it is not acceptable to the public because the deformations that we talk about damage many things, so that we have to make sure that this can be avoided, or we can determine that in advance whether this will happen or not. Actually, this should not have happened because the earthquake level was not of the design level, not MCE. It was much smaller than that. So for this building, this should not have happened for that particular earthquake. There are many reasons why it happened, but in any case, it's not acceptable. So the first thing that I want to emphasize, I have mentioned this before also, is why the performance-based design, especially for tall building, generates a better result or better, I should say, confidence level than a traditional design. And one of the important factor for that is this concept of converting or estimating the nonlinear response from linear response. Because we are not able to do that pushover curve for each structure, the building codes try to estimate it. So they estimate it by two factors in the code. One factor is called response reduction factor, R, and second factor is called capacity, the strength, over strength factor, omega, you know about that, right? So both these factors are the one that combine give us the estimate of that pushover curve somehow. But the problem is that they are often very wrong and they cannot be estimated reliably for various systems, and most of the time they are too large. So especially for tall buildings, this R factor tends to be quite wrong. I think you have seen this presentation many times. You were there with the Ron Clemency presentation also. So he also mentioned about that. So this issue with the R factor is one of the reasons that we try to do more than the code. We are not saying that the codes are bad, just that they are not applicable in all cases. Their intention is very good, and their intention is to help ensure public safety, provide formal legal basis for design, and we assume that if we follow the code, it will be okay, right? But we are not sure. We cannot. The most important thing is they are not explicit, and I keep saying that many times that they are not explicit. For example, if you change any small thing in the code, I would like to know what is the effect. I would like to know why the spacing of the stirrup has to be 10 centimeter in the beam zone. Why not 11? Why not 12? Can I make it 15? Can I make it 13? I would like to know. I would like to challenge that provision. But the code does not give me the ability to do that. It just tells me you need to make it 100 millimeter in that confinement zone, right? I can understand that they have done research and they've come up with that, but I would like to know what happens if I make it not 10 but 12. But if I change to 12, there is no equation, there is no method, there is no provision in the code-based procedure to tell me what is the effect. I can only say I follow the code or I don't follow the code. There is no in between zone that I can stay. So either I'm wrong or I'm right. But in reality, things don't work. Like for example, look at these limits: 4 dB, 2 dB, 8 dB. Everything is a multiple of 2, and reality is not a multiple of anything. Reality is continuous, right? Things change not like that. Things change continuously, right? So because of that, all these arbitrary limits become questionable. So we would like to know these questions. I raised this before also. First question is, are all building codes equal? Right? No. You already know the answer. But then the question is, which one is more equal than the other? Right? They say, people are not equal, but some people are equal, some are more equal than the other. It doesn't work, in this case. So that is the first problem. They all differ, so they all cannot be right naturally. So we would like to know which one is more reliable. I mentioned, and again I mentioned many times, the structure behaves the way it behaves. It behaves. Only two things the structure knows, no matter where it is, who designed it, who you didn't design it. People just built it. In some places, just contractors or builders or masons or other people just go and build something. In an earthquake level, earthquake really doesn't care who designed it, what code was used, use ETABS or SAP. It doesn't care. It just cares, this is a structure here, what is the column size, how many bars are there, what is the behavior. That's it. So the structure is going to respond based on what you built, not what procedures you use to arrive at that design. It actually doesn't matter, right? If you put 4 bars, and whether somebody just estimate 4 bars or you did a million calculation to arrive at the 4 bars, these are 4 bars. The structure is going to behave based on 4 bars on site, not on how we arrived at it. Correct or not correct? So for that reason, no distinction between the codes when the structure performs during a hazard. It only cares about what we put there. So we should be able to evaluate the structure based on that. Another thing is the codes change every 3 years. So we cannot go back and keep fixing the structures every 3 years because now they don't follow the code. Obviously, that doesn't happen. So because of all these reasons, there are many concerns. I mentioned it before also, that people want to know more. Public wants to know more explicitly what's going on. And so we, like I said, don't hide behind the code. We don't want to hide behind the code. We don't want to say, I don't know, I follow the code. This sentence should not come out from a structural engineer's office or his. He should know or she should know what they have done, right? And that is the reason why so many engineers are now moving toward performance-based evaluation, because they will know the details that otherwise they would not know if they didn't go through this procedure, right? Clients will know, builders will know. We have the answers for them. We have the answer that if you change the stirrup dimension from 100 to 120, what is the effect? That kind of answer we should have. We should be able to answer that. So that is the reason performance-based design came into being. So these are the shortcomings of the codes. Number 1, traditional codes govern design of general non-normal buildings, and it is true that 90%, 95% buildings which are less than 50 meters may be okay, right? But they're not, because in every earthquake, mostly these are the low-rise buildings that get damaged, right? You have seen every earthquake. How many times have you seen a tall building fall down in an earthquake? Very rare, almost never. Low-rise building. So it's actually not really true, but normally we believe that the codes govern about 95% of the building that we build. So these are prescriptive in nature. That means you cannot do an explicit check. And then, most importantly, they permit a limited number of structural systems. They do not allow you to design something that you want to do because the code factors are based on certain assumptions and certain limitations and certain testing. So if your structure is outside those, then the codes will tell you you cannot do this. For example, there are many most common, most popular restriction is, what is the most popular restriction?
Flat slab.
Flat slab in earthquake zones, right? But now we make them. In Philippines, most of the buildings are flat slab, highly seismic zone, tall buildings, because we can understand them better and we can prove that it's okay to use that. So this is one. There are many other provisions. What is the second important provision that we are studying this term? I have one thesis on studying that particular provision. Very important one also. Backup frame provision. That means the building codes say that if you are building a tall building, 25% of the forces must be resisted by frame, even if you have a shear wall there. So shear wall cannot be designed, the frame must be designed to resist 25% of the lateral loads. That's an important provision, right? But in reality, it is very, very difficult to do that because core walls are so stiff that they can take about 80% to 95% of the loads. So if you try to design the frame for 25%, you have to increase the reinforcement for no reason, just to follow the code. Useless money spent or useless column sizes increased because we have to follow that provision. Nobody likes that provision. And if you use performance-based design, you can prove that only core-based buildings are fine too, right? So there are many other provisions. R factor, you don't have to use what the code is saying. You can find your own R factor from nonlinear analysis. So similarly, the omega factor, you don't need to use omega factors also in PBD, right? Because you're dealing with real demand versus real capacity, including the increased concrete and steel strength. So do not include framing systems appropriate for high-rise buildings. So codes do not handle many of the framing systems that we use in tall buildings. That's why it's difficult to use them. They are mostly based on elastic method. And I've shown you that inelastic nonlinear is very important, especially for earthquake. They enforce uniform detailing rules on all members. All beams must follow confinement, no matter where they are, no matter how much demand you have. All columns must have confinements. But in reality, that's not true. Only a few zones, few floors, few locations are going to yield during an earthquake. So you only need confinement in those locations, not everywhere. Not all beams are important, not all columns are important. So uniform application of rules is unnecessary, right? That's another important. Enforce unreasonable demand on distribution rules, as I mentioned, 75, 25, and other many rules like that. And then do not take advantage of recent computing tools. Now we have nonlinear analysis tools that we didn't have before. So the codes do not take advantage of those tools. And in reality, these things are very important because really speaking, out there means if you go to the field in the design offices, 90% or maybe more percent of the engineers do not know nonlinear dynamic analysis. You people are graduates already, right? You're not students. You're already undergraduate. Many of your friends are already working in design offices. Do they know all this? No, because you also don't know. So how can they know? So it is understood that a majority of engineers like yourself who are graduates and already working in offices do not know this. So obviously then codes have to come in and help them until they know. But we are hoping that once you graduate from here, you know and you have the choice to make between that and this, right? Not many universities are teaching PVD also, I can tell you, right? In many universities, after you finish graduate and most, master's degree, they just repeat the courses that you have already taken in undergraduate, right? So not much change. I have seen, we interview so many people from UK, from America, who come back from universities, have no concept of nonlinear analysis or performance-based design, right? So anyway, so this is important. Computing tools, you should use them to the maximum. So that means we can improve this whole thing. And our method, this slide you have seen from many people many times, and let me emphasize one more time that R factor only is reasonable for first mode, and R factor is more reasonable for bending moment. R factor is not so reasonable for higher modes and not so reasonable for shear. So that is the reason that R factor calculation sort of distorts the results. And many times you will find that especially for shear demand, let's say here, that the true demand, that means nonlinear analysis demand, is more than the core demand by 2-3 times. So when I talk about this one in the field outside, suddenly engineers say, oh, but then my structure will become very uneconomic, very costly, right? That is true in a very limited way, because only some part of the structure will be affected by this one, not the entire structure, only shear. But you can reduce the demand in bending. So normally, as I might have mentioned or not, I forgot, when mostly the engineers design the building and bring it to us for performance-based design, the first thing we do by closed eyes, or I shouldn't say closed eyes, we take the vertical reinforcement from the shear walls and put it horizontally. And we take the reinforcement from the beam, horizontal reinforcement, reduce it and increase shear without doing anything. If you just do that, your structure's performance will increase without increasing cost. Because they are putting too much reinforcement in the wrong places in the wrong manner. It's not that the reinforcement we are going to increase. We are just going to put it in the right location in the right manner. So if you shear wall, if you put a lot of vertical reinforcement, what will happen? What will happen? If I put a lot of vertical reinforcement in a shear wall, what will happen? Say something. What will happen if there's a lot of reinforcement? No. Talk like engineer. Don't talk like that. What will happen?
Let's start that.
No. What will happen if I put a lot of reinforcement in a wall cross section or a beam cross section?
Brittle failures.
No. Step by step. Rational mind. Think cleanly. I will go for. What will happen if I increase the reinforcement, vertical reinforcement in a shear wall? I want the right answer. Okay. What will happen? What will happen? What will happen?
Very stiff and we can reduce.
No stiffness. Stiffness has nothing to do with that. I'm putting reinforcement. What will happen?
Changing the loading.
No loading. It will not change the loading. Wrong. My goodness. What will happen? Nothing will happen.
Yes.
Nothing to do with flexibility. What will happen? No. What will happen? Yielding strength. Okay. So hold on that one. Wait. Okay. What will happen? What will happen? No. Overturning moment. Yeah, you are getting a little bit close. You are a little bit close. What will happen? I want the exact answer. What will happen? I'm not getting it. When you agree?
Shear and bending capacity.
Okay. Now you're too late. Your capacity test. What will happen? Please. 40 people, give me one right answer.
Plastic deformation.
No. You were right, you don't make it wrong. Yeah. What will happen? What will happen? What will happen? Yes, true, that is the consequence, but I want the first answer. What, you're very close, but not right. When you put a lot of vertical reinforcement on the vertical in a shear wall, the moment capacity will increase. Is it difficult to imagine that you put a vertical reinforcement in a shear wall, the moment capacity of the wall will increase, right? So you are a little bit correct that the yield strength or yield capacity will increase. You're also correct that the failure might shift to shear, but I want the right answer. Step number 1, moment will increase, moment capacity will increase. Once the moment capacity increases, what will happen? Next step, I want to go to the next step. What will happen after the moment capacity increases and you have an earthquake?
Difficult for failing shear.
Don't go to the third step. Step by step. You people are not step next. If the moment capacity increases, what will happen?
It can take more ropes.
Okay. Give up. I give up. No, the other. I just showed you that comparison of that curve, pushover curve, right?
We need more to resist for shear.
Yeah, okay, you people are now getting there, but I want a very clear, okay, let me explain to you. This is what will happen. This is what when you put a lot of reinforcement, vertical reinforcement in a column or in a shear wall, or a lot of horizontal reinforcement in a beam, the moment capacity increases. When the moment capacity increases, the moment curvature becomes higher for a certain curvature, right? So when the structure deforms, it can take much more moment than before. So if that is the case, then if the shear capacity is not enough, then shear failure will happen first, right? So that means that the structure has become stronger in bending moment and correspondingly weaker in shear. And earthquake forces are always going to be larger than the capacity of bending moment. So that means your shear will fail much earlier. So you people understand a little bit concept, but step by step, flexural reinforcement increases the moment capacity and change the moment curvature curve, and hence the total forces that the structure can resist will increase, and those increase in forces will make the shear fail first, because moment you have already provided enough capacity, right? So because of that, I was saying that when the people come with 4% reinforcement in the shear wall, we say don't do that, make it 1%. Take that reinforcement, put it horizontally to make it strong and shear, right? So many times actually we have to take the reinforcement out to reduce the moment capacity, so that the ductility will increase, so that the total force demand can come down and shear failure will not happen before the moment failure. So that is why it's not always uneconomical. It's just that we put the reinforcement in places where it will be more useful, right? Because we know exactly what's happening, right? So that is the advantage of PVD, one of the advantage of PVD. So this is the overall system for performance-based design. So the performance-based design, please watch this carefully. I think you have seen it before, but see it again. There are two real levels in a structure's life. One level is service level. Now I'm talking about earthquake for now. It is applicable to others also. But one is a service life, daily. That means a service level earthquake or service level wind or service level loading, live load today. This is service level. That means things that will happen routinely to the structure. For that, we should be checking the corresponding strengths and DC ratios, demand capacity ratios for that without multiplying by any factor. No need. Real loading, real response and see where we are, right? So this is and then we say, okay, at service level, there should be no damage in the structure because these are the earthquakes that come very often or loading that come very often, so the structure should survive them without any problem. So no factors, you check the real capacity, real loading and compare them. If this is fine, it is fine, right? This is the code arbitrary level where they multiply the loads by some factor and bring it here. And then they check for some assumed strength level. This is not real. So for us, that does not exist. That does not correspond to any life stage of the structure. It's not part of the life cycle of the structure, that loading. Then there is this life cycle loading when the structure experiences something extremely extreme, something that maybe has a very low probability of coming, 2% or less, right, in the lifetime of the structure. Extremely low probability, but we still don't want the structure to fall down for that probability. So we check this collapse prevention for that level and serviceability for that level. Once these two levels are okay, there is no design level anymore. There is no need because that corresponds to nothing. Correct? So if you ensure that normally the structure will be fine and you also ensure that it will not fall down in extreme cases, then that means it's okay. Don't worry about the design arbitrary levels. So that's that is now the way the performance-based design work. For earthquake, this is 50 years return period. This is 2,500 return period. Same is the case with wind. This is maybe 10 years. This is 1,700 years. So we can work with live load. We can also see the same thing, normal live load and live load when everybody is dancing in this room, right? 200 people, that maximum capacity. You can check that, right? How many people can you pack in this room edge to edge? That will be the extreme case. And you can check for that case that it should not collapse. But no need to multiply the live load, arbitrary live load of whatever number by, we don't even know where that come from, right? As I mentioned to you, what is the live load typically for a university classroom? Nobody remembers. 60 PSF. Okay, 60 PSF is about, okay, let's say 60 pounds per square foot, right? 30 kilograms per square foot, which is equal to about 300 kilogram per square meter, correct? So 300 kilogram per square meter, and this room is 6 meters by 10 meters, 60 square meter, multiplied by 300. How much is that? 1,800 tons, right? Or 1,800 tons, 18 tons. How many tons? Nobody can multiply anymore. 18 tons. Okay, 18 tons. Okay, okay, 18,000 kilograms. How many people one person is how many kilograms? 70, 75, okay. Not talking about you, 50 or 45. That's 45? Right? Okay, let's say 75 kilogram, average person, right? Divide that by 18,000 divided by 75. How many people are there? Use your calculator or phone. 18,000 divided by 75. 240. So you need 240 people in this room to reach the code specified 60 PSF load. Can you imagine 240 people here? And then you multiply it by 1.7, which will be, how much is that? 480. Can you imagine physically packing 480 people in this room to reach the design level loading, right? So it's ridiculous, right? But if you want to check reality, you say, okay, how many people can I pack here? 200. You check the design for 200. That is your extreme level. Service level is what we are doing now. 60 people sitting here. Let's say So that's how service level and the extreme level can be combined to do the assessment of a structure for any loading. Realistic, not arbitrary. That makes no sense. 480 people. You know, that's the whole AIT's full batch intake, right?
So for the largest earthquake, do we consider 2/3 of MCE for the collapse level?
No, this is real earthquake, MCE. This is called MCE, maximum credible earthquake. 2/3 is design level. We don't consider that because what is 2/3? Why 2/3? That's the thing that I'm trying to say. 2/3 is a design level, arbitrary level. What does it mean 2/3 of a maximum earthquake? Why not maximum earthquake? Why not? So the criteria can be changed. So where is that diagram? I think I still have it.
So is it another reason that when we draw the spectral acceleration, we
Yeah.
consider the maximum earthquake level of that zone? That's why we may consider 2/3 in statistics.
No.
Like when we consider the spectral acceleration, we consider all the maximum earthquake accelerations to draw the spectral curve. So it might be another reason.
Yes, 2/3. No, that is already the average. That is from the design from the average of all the earthquakes already. 2/3 is only to bring it down to a design level, arbitrary level. So my point is that these are the real levels. So this is corresponding to MCE, right? You can say 2/3 is here, but what is that corresponding to? Why do we need that? When we already check for this, we check for this, we can check for this, we can check for this. And we don't need to call them anything. We can say this is frequency for 1 times in 50 years, 1 time in 200 years, 1 time or 400 500 years, 1 times in 2500 years. Whatever you define it clearly. Don't use factors. Be explicit. You can say that I would like to design my structure for an earthquake which comes every 500 years and I would like it to be like this. Okay? Fine. We can do that. This is the intention of the code, by the way. But we never check it. But you could. Somebody might say, like a nuclear power plant, you know the Japan case, the Fukushima. You know that, right? Okay, some people are saying something else. Fukushima reactor earthquake came and damaged it. Because of that damage, maybe $20 billion loss to Japan because of that leak that happened. So for that kind of structure, you can say, MCE, I want operational. You can say that, right? And you can design it to be like that. Nothing is preventing you from designing a structure to be operational, even at MCE, like hospitals, like fire station. Because in MCE, you don't want the hospital to be damaged. You don't want the fire station to be damaged because you need them, right? So the criteria can be changed depending upon what you are designing, what is the purpose. Rather than giving an importance factor of 1.5 to something, you actually move your performance criteria to the required one. Then it becomes real. Some client may say that, okay, my house, I don't want it to be damaged for any possible earthquake, right? If you are using code-based design, you cannot even guarantee that. Let's say if you are using code-based design and somebody say, I have all the money in the world, design me a structure that will not collapse, forget about collapse, that will not be damaged at all during the strongest earthquake. Your codes cannot help you there, right? Because you are not sure. How can be sure? But performance-based design, you can be sure because you simply change the criteria. This one. These are the performance criteria that you can check for various things. And you can just say, okay, measure to occupancy here, and somebody says, I want this to be for a certain level. You design the cross-section so that you get these things. So these are the limits on the moment curvature curve or moment rotation curve that you can check. So You plot this force and deformation curve for every component, and you can check every beam, every column. Where is this column? Where is this beam in terms of the performance? Not only the whole structure. You can check and you can say, okay, this beam I want here, this beam I want there, this beam I want there. Somebody might want to say, I want to make a strong room in my building, right? That rest of the building, I allow it to damage, but this strong room where I'm sleeping or I'm putting my money or whatever, or computers, should not be damaged. Then you can go to that strong room and you can design those beams only for a higher performance than the rest of the structure. So this ability to explicitly design things to a required statement, you cannot get from code-based design. Only can get from the explicit performance-based design. So this is the main. This is for non-critical members. This is for critical members. So you have all these limits, linear classification of actions, and then. So that's the summary, right? Any questions? Yes. Ouch! I always forget. Tables are not designed for sitting here.
So, in performance-based design, we are considered to response, and based on that response, we design our building.
No. Performance-based design is a check of the performance. You don't design. Actually, the term is wrong. We normally call it PBE. We don't call it PBD. It should be called performance-based evaluation. Because this is not a design procedure. This is a evaluation procedure. Because reinforcement is designed first, and then you check it. So this is a verification procedure. Trial and error, verification. So this is a design evaluation, design verification procedure to determine what is the performance level of a structure that has been designed already. I showed you just now for the first slide. Short memory. Okay, let's go to the first slide so that you can remember what I'm saying. Fertility. Do not forget this slide ever. Memorize it in your head, because you can see from here that you are starting with a known design to check the performance. That means the reinforcement, the material, everything has to be known first before you can do the performance-based evaluation. So the better term is PBE, performance-based evaluation. That you are checking the performance of a system that has already been designed. Normally we design it for service level and check it for the collapse prevention. Or you can design it for DBE or the code level and check it for performance, either way. But we find it now unnecessary these days to design it for code level. It's meaningless. So you better design it for service level and check it for collapse level. These two checks are called PBE.
So is it really possible that in a same building have a different performance level?
Yes, of course, of course. Each member, each column, each section can be designed to have a different performance level as required. Why not?
I'm confused about we usually design the weak beam strong column way. So if we provide different capacities in the each beams, so is there any possibility that some other column might be?
But that possibility is the one that you have done the analysis to show that possibility. That's my my point exactly. That once we do the nonlinear dynamic analysis, you know everything about the structure. So that possibility is already in the analysis results. So you can see whether that possibility will happen or not happen through the result. That's why we check. When we do the performance evaluation, we don't just check the final response, overall response. We check every member, every column, every beam is checked to make sure that that doesn't happen. And sometimes we find, it's interesting, sometimes we find that some columns in a building or some beams in a building are actually exceeding the limit. They don't have good performance. But we let it go. Because as long as this overall structure is safe and their yielding or their damage is not going to cause any problem, we let it go. Because it doesn't matter. As long as that thing does not cause any damage, any problem, you let it go. If one beam is yielding somewhere and it is not affecting anything else, it's okay. Because this is a collapse prevention analysis. So if it is not leading to this collapse of the structure, that damage is acceptable. Only when you have so much damage that the building will collapse, we don't allow that. So that's the whole idea, that you can set the performance criteria clearly between yourself and the client and a third party who will check your design. But please remember, performance-based design cannot be done by one team. Must be two teams. One team will do it, one team will check it. So every time we do a performance-based design, Ron Klemenzik, his team checks our design. And when they do the design, we are checking it these days. Now it's become such that their design is coming to us for review. Before, our design used to go to them for review. That's how we learn, that's how we cross-check, make sure that we are not making, because this is very important. We are going beyond the code. So some other people have to make sure that we are not making any mistake during that time. So peer review, cross-checking is part of the design PBD process. Any other question? Yes.
Displacement-based design,
Yes.
force-based design,
Yes.
and compared to performance-based design, whether it is the same approach or
Yeah, performance-based design is an extension of the displacement-based design. This is an extension of I would say the next level of displacement-based design. Pushover, this is displacement-based design because we are displacing the structure by a certain amount, generating the pushover curve, and we are checking the performance. So this is actually displacement-based design. Because we are not actually applying a force, we are applying a displacement pattern corresponding to mode shape. So that's why it is called displacement-based design. That we are displacing the structure in a certain pattern, forces are secondary. So force-based design is when you apply the real forces of earthquake multiplied by some factor, then you calculate the reinforcement. That is force-based design. Any other question?
So about the first picture that you showed of the building in Nepal.
Yeah.
So was it just designed for the code-based approach, or
Yes, code-based approach.
so just that they followed only the code-based approach?
What do you only? Everybody follows only the code-based. 99.9999999% engineers follow the code-based.
About the reason of that failure.
Reason of the failure is interesting. Many. Okay. Next time, remind me. We will talk about, because this is part of the discussion. That Nepal's earthquake. We have a lot of information. I don't know if Dr. Spenning has explained that to you or not yet.
About the response.
Response spectrum.
No. Nepal case, that earthquake, whole history and the why it happened that way and why certain building, the whole case study of Nepal. Did he?
He just told one thing, the response spectrum for the ground of Nepal is different.
Yes, but what does it mean, different, and how does it affect everything? And okay, I will talk about that because that's important lesson in understanding the relationship between the response spectrum, structural performance, and everything. It's an interesting study, so we will spend some time and answer your question at that time. And why why in that building, one building got damaged more? It's a beautiful, I'm so sorry. I apologize. It's not a beautiful picture, but it's a very informative picture because there are one 17-story building, 12-story building, and 9-story building. And the level of damage is very different in each building, right? And it has to do with the national period, it has to do with many things. So it's like a textbook case. If you look at that building, you say, oh wow, the theory really works. Unfortunately. Okay, any other question? Yes, please. Wind also same thing. So for wind, you can use this loading corresponding to the wind pattern, wind loading pattern. So if you know the wind loading, you can use the same. It doesn't matter. Performance-based design, actually, we mostly use it for earthquake because earthquake we design for inelastic forces, but actually can be used for anything. Like I said, live load. All we need to know is loading pattern or loading hazard pattern and capacity of the structure, and then we can compare. This could be blast. Currently, one of your senior is looking at the performance evaluation of a building. If one column is suddenly broken, what happens to the building? Will it collapse or will not collapse? You know, interesting thesis, very good results.
Might be depend on locations.
Yeah. So he studied also, he tried to break all the columns in the building one by one and see which column has the maximum effect and how much, and nonlinear dynamic performance-based analysis for linear stats. So he did a lot of work, very good outcome. So we always look at these kind of things. So it's an event that a column is broken. What will happen to the building? What can we do to prevent the damage from spreading to a large part, right? Those kind of things. I plan to present to you my last class about the current theses which are going on, right? At least with me. So you get an idea that what kind of research is being done, and especially will help you to decide something about your own thesis next year, next term, right?